we have a vote matrix A, an incomplete vote matrix, as I said yesterday, meaning that some of its entries are unknown. This is an n by m matrix, which has both real numbers and possibly some not numbers, meaning that some entries are not known. We establish a rank R of the approximate matrix of the model, and we want to define two matrices that yesterday we called C, which has as many rows as there are. Okay, we can interpret this as a user by items matrix. So C has as many users, as many rows as there are users, and R columns. And P has as many items, as many rows as there are items, and R columns. So we want to find these matrices so that we can approximate the entry Aij by computing the sum of the overall average of all entries of A, of all known entries of A, plus what we call the bias of user I, meaning the row average of user A, of matrix A corresponding to user I, plus the column bias of item J, plus a second order correction which is the sum, the dot product of the ith row of matrix C and the j row of matrix P. And if we call A prime ij this approximation, we want to minimize the overall error E, which is computed by adding up all errors in all vote predictions. Meaning that I add for all users and items such that the vote is known, so for which the element Aij is a real number, and of Aij minus Aij prime squared. Okay, here I write it on this side of the board. And actually, okay, let's see this. So to do it, I have to compute the partial derivatives of the error with respect to the generic element that I want to control. And this is simply, well, not really simply. Okay, I need more space. Let's write it here. So actually, you can write E as the sum of those i's and j's of aij minus mu minus di minus dj minus the sum on k of cik dj k squared, so that the partial derivative of E with respect to c ik is the sum over j of this dij minus mu minus di minus dj minus sum on, it's not the same k, so I'm going to call it k prime, c I k prime, b j k prime, times the derivative of the content with respect to cik, which is minus b j k. This is, of course, twice this. Okay, this is the derivative with respect to c, for the same reason. The derivative with respect to the generic element pjk of the second matrix is the sum over I of aij minus mu minus di minus dj minus sum of k prime of c I k prime b j k prime times minus c I k. So what I propose now is, okay, let's find some small data set to test this, and let's see what we can obtain. So much better. Now, I found this data set. If you look on Google on Jester data set, you are sent as a first result to a page related to an online joke recommender system. Those people collected 100 jokes and they built up a system asking some evaluation of these jokes by users. Well, okay, so we have the original data set has 100 jokes and 73,000 users who went to the web page that asked them to rate them. Of course, many users rated a few jokes, but this website is also providing a rather dense data set. The first one, just data1.zip, taking those 24,000 and so users who rated 36 or more jokes. So we have a significantly dense matrix of evaluations. Let's see how the file is encoded. So let's take, so I took gesterdata1.zip, I'm going to save it somewhere. Probably in the downloads directory. Okay. We can unzip this file. We will find that it's an Excel data file. Okay, gesterdata1.xls. So we can open it. I hope that we can open it with something. Okay. So I launch Open Office to see how it's done. Let's open gesterdata1.xls. Okay. This is the rating matrix. On the columns we have the jokes. So they are 100 columns. Some values are 99, which encodes a missing value, okay? Meaning that this user, the user at the third row, user 3, did not rate a joke at column K. Ratings are on a scale between -10 and +10. So -10 means I really dislike this joke, while +10 means I cannot stop laughing, I assume. Okay, you see the first column is different. They are all numbers, probably it's the number of rated jokes in the row. So what we are interested in are the columns from B to the last one. I want to write a Python script to look at this matrix. So the first thing I can do is save this matrix with a different file type. I would use a comma separated values file, a CSV. Okay, I want to save it in the current format. Now here it's asking some more questions. I'm okay with using a comma as a field delimiter. we should not have any text because they are all numbers. So the text delimiter is useless. Okay. And now, okay, here we also have the just data1.csv file, which is, as you can see, a series of long rows with numbers separated by commas. Okay, so now we want to work with this file. So let's create a Python script for that. We can call it recommend.py. Okay, and now we have, well, first thing we want to do is open that file and read those data. So, okay, opening a file is very easy. Let me just use the name, just the dash data -1.csv. I want to read it as I just want to read it. Python also provides a utility for working with the CSV files. So you have a CSV module. Of course, I don't remember the commands, but we have the internet for that. Let's just look for Python reference. No, let's just look for Python CSV module. Okay, reader. So I take a CSV reader, I build it on file F, among the parameters I should be able to also add the delimiter, which in our case is a comma, and this is it. Now, we just iterate on all lines in the CSV file. The CSV file is called CF. But what do we do with the lines? Okay, the CSV reader already returns lines in terms of lists of elements. Now we want to take every element and store it in a matrix. However, since the matrix has many unknown values, undefined values, rather than using a complete representation of the matrix, I will use a sparse representation. So for me, the matrix A will be a list of triplets where every triplet is a row column, index column, and vote, in order to eliminate all those entries that are unknown. By the way, we need also to count how many rows and columns there are. So let's start by setting the number of columns to 0. let's set our matrix A to the empty list. And for every line, we want to add to the list A all the entries that are, if you remember, that are different from 99, which was the unknown value encoding in that matrix. So, for the line, for all elements in the line, we want to, of course, remember also the column index M. And for all values V in the line, well, actually, if you remember, the first element of the line was just a counter, so we need to skip that. So we only start from the element having index 1. And for all of these values, okay, the CSV reader returns a list of strings. So V is a string containing a number encoded in it. So let's call A the corresponding float. And the idea is that if A is 99, then we have to skip it. Otherwise, we have to store it as a valid vote. So, just to be sure, let's say if the value that we just read is less than 90, then we have to store it in matrix A. So we append in matrix A, so I'm using an uppercase A for the matrix and the lowercase a for the single vote. And I want to append the triplet composed by the row index n, the column index m, and the vote A. Notice here the double parentheses because, okay, the first pair of parentheses is for the function, and this triplet is the element that I want to put in the matrix. Of course, for every V, I want to increase the column counter, and at every line, I want to increase the row counter. And this should complete the reading of the file. Let's just test it by printing the matrix A. I just add here some code for the automatic choice of the interpreter, and here I change the mode of recommend.py so that it's directly executable, so that I can invoke it as recommend.py. Okay, first problem. Actually, the keyword in Python is just open, not fopen. Okay, now the Python script is reading the list, and now it's writing it. Okay, at the first sight it looks almost right. Okay, every element is a triplet, user index, joke index, vote. Of course, the float conversion looks a little wobbly, so this is 4.42. For some reason, the conversion or the printing function leaves lots of decimals. Anyway, this is what we want. So now we have a matrix, not really a matrix, a list A that encodes the known values of matrix, of the vote matrix. Now, from this matrix, we have to compute a few values. We need to know in advance the arithmetic mean of the votes moved, the bias of every user, and the bias of every item. So, well, let's just do it. So we start with a mu equal to 0. We declare a vector B, which will contain the biases for every user, as a list of zeros. How many? As many elements as there are users. D is the same, so it contains zeros, one for each item. Now, actually we will also need to count the number of rated items for the number of ratings for every user and every item. So let's call the vectors NB. NB is initialized as a number of zeros, as many as there are users, and ND as many zeros as there are items. So now, for every triplet I, J, A in the list A, okay, we just need to add the relevant, add the vote A to the relevant items. So, for sure, we need to add it to mu. We need to add it to B of I and to B of J. The vote must enter in the overall average mu, on the average of user I, and on the average of item J. And of course, we need to remember that the number of elements evaluated by user I must be increased of 1, and the number of users that evaluated item J must be increased by 1. So that, after computing this, we just need to divide mu by the total number of items, the total number of votes, where the total number of votes is simply the length of the list A. Then, for all users I, now remember there are n users, B of I must be divided by NB of I, so that we get the arithmetic mean. Then we do the same for j in the number of items, and we also divide the bias of item j. So now we have the starting point for our computations. Okay. Now, what we have now are that part of the vote that does not require the interaction part between the matrices C and P. Now we have, well, let's see. Suppose that we use this simple model, so without matrices C and P, but only overall average and user and item biases, and we use them to compute, to approximate the vote. What is the overall error that we make in this case? We can check, of course. So, let's see. Let's see what is the overall error that we make in this case. So let's start with an error equal to 0. And then, for every vote in matrix A, okay, I see how many, what is the difference between the forecast vote and the actual vote. So, the forecast vote, let's call it A1, is equal to mu plus B of I plus D of J. The error that I make in this case is simply A minus A1. Now I can simply add its square to capital E. And finally here I can just print okay, let's call it this E2 because it's actually a square. Okay, it's not that important actually. Now I need to take a square root, so I need to import the math module, and I want to compute the square root of E2 divided by the overall number of entries, of known entries in A, which is the length of A. Okay, this should give me an error that I obtained by only considering this rough model of computing votes. Oh, it takes a little to compute because we have to read lots of numbers. Okay, anyway, we have a response, 4.62. 4.62 is actually, well, not really a good number, of course. It means that by estimating the vote of the user by this very simple model, we tend to miss the correct answer by an average of 5 points, which is a lot. Actually, the user evaluation is between -10 and 10. So they are 5 points out of 20 possible points in the scale. So this is an error of 25%, more or less. Okay. We are committing a 25% error in doing this. Of course, we can refine the model. Let me do one thing first. Let's not read all the lines in the file. The file contains almost 25,000 users, which are a lot and takes time to read. So let's say that I only want the first 1,000 users. So I break out of the reading loop after 1,000 users. I only read the first 1,000 once. Here at the end I can also close the file F. So that now, sorry, F point close and nothing else. So we get a faster answer, okay, which is still around at 25% of the scale. Let's see if the finer model that uses matrices C and P to model the users works better. So let's start from right after we computed the overall arithmetic mean and the user and item biases. Now, to continue, we need to set up two matrices called C and P. So these are complete matrices, so I define them as lists of lists, where every list, okay, we can start with a random number. Okay, so C will be, of course, we need the random module here on the top. Random.random returns a number between 0 and 1, a real number between 0 and 1. So I can multiply it by 2 and subtract 1, so that I get a number from -1 to +1. And I want to do this r times. Remember, R is the number of features, so the number of columns of matrix C. I will define it above later. This is a single row. Then, of course, I want n rows for matrix C. So here I create a random matrix, a random n by r matrix. The same for matrix P, with the only difference that I need as many rows as there are items. And I prefer to use index I when I speak of users and index j when I speak of items. Okay, we must remember, of course, here at the beginning we define r. For example, let's set it to 5. Remember that a very small r accounts for a very rough approximation. r equal to 0 would mean no matrices, so it accounts for 25% error. Let's see what happens if we set those matrices and we set a reasonable number for r. And next, after defining these matrices, we need to repeat many times a step of moving against the gradient. So the gradient descent step that uses the formula that are behind the screen now. So for step in let's call end steps another parameter which I define here. Saying that I want to repeat it 100 times, for example. What do I want to do? I want to compute all partial derivatives of the error with respect to all the elements of C and P. And to do this, well, let's define two matrices which I will call DC and DP, which will initially contain zeros, and where I will accumulate all the contributions of single terms of user I and item J in order to determine the final derivatives. Remember that each derivative is a sum of terms. It was behind here. Let's see if we can see both things together. It will be hard, but okay, we need to take these two formulae and put them in the code. So to do it, we just need to iterate through the list A, or the spatial representation of the matrix A. Now, up here was I just need to compute this part. So let me call S this part. So for a given I and J, S contains the actual vote A minus mu minus B of I minus D of J, and then for K going from 0 to R minus 1, I add to S, actually I subtract from S, C I K times P J K. So here I computed this S value. Now, so this is what I'm calling here in the code DC of I k. Okay? This is the code, the name in the code of this derivative that I'm going to compute. So in dc of I k, I'm adding this term of the sum for the particular value of j that I have in the iteration. So it's s times let's write it as it is there, minus p of just a moment. Of course, I need to put this in another loop. Minus p of j. Okay. Okay, there is also a 2 in front. So let's put it here. For the same reason, dp of jk has 2 times s times minus c of ik. Okay, after this loop that covers all these sums, dc ik and dp of jk will contain the derivatives, so the gradient of the error function. Now I need to move cik and pjk against the direction of those derivatives. So, let's see. For I in the number of users, well, let's put at the beginning the common loop of the two. Oh, sorry, here of course it's X range of R. Okay. Very dangerous errors. Okay, here we just take C of I k and we okay, we must go against the derivative, so we subtract from it some small value eta times the size of the derivative dc of ik. We will need to define a small value eta next. Well, let me write it now. So eta can be 0.0001 for the moment. Next we will see how we can set it. Of course, if it's large, convergence will be faster, but if it's too large, then the system might risk to oscillate or even to diverge. The same here must be done for the product matrix P for J that ranges from 0 to n minus 1. So the matrix P of Jk is reduced by something that is proportional to the derivative, like this. Okay, after we have done this, we have that the values in the matrices C and P should be such that the overall error is slightly reduced. And step after step, we should reduce the error to a local minimum. How do we say that? Well, let's just take the previous code for evaluating the error. Let's put it inside the loop, and let's modify it so that we also get we put also the matrices C and P in the loop. So here, again, the sum of square errors is initially 0. For every vote in the matrix, I start by computing the vote as the approximation here. Now I also add the sum, the dot product of the two lines of C and P. So for k in the range from 0 to r minus 1, I add to A1 C I k times P j k, so that I get the vote forecast. I put the difference into E, I sum everything, and finally I can write the square root of it. So now, step after step, we should expect this error to go down. Of course, I might have committed lots of errors, and also syntax errors I see in line 47. Okay. Okay, now as you can see, step after step, the error is reduced. So, starting from almost 5, the system is recomputing the matrices C and P so that they slightly contribute to reduce the overall error, which is now about 4.2. So we are going towards 20%, slightly more than 20%. This is still a rather large number for a recommender system. But, okay, we need to consider that this kind of evaluations is rather noisy. In fact, this is considered a rather hard data set because, you know, when people, for example, rate movies or books, they do it after actually watching the movie and the book, and they have a rather precise idea of how, if they enjoyed it or not. Reading a joke is something much faster. So the response tends to be a little more random. Okay, anyway, we are converging towards the 20%. Now we can make some experiments. For example, what happens if we reduce the number of features, so the rank of the approximation? If, for example, we use only one feature for every user and one feature for every item, so that C and P are actually column vectors. Of course, computation will be faster. And as you can see, it's not much worse. I mean, it's converging to a number which is larger, 4.28 more or less, while before it was, I think, 4.121. Okay. So the idea is that the more elements you put, so the deeper you make your matrices, the better the approximation. But of course, the computation starts to be slower. In fact, I expected some improvement by moving R from 1 to 2. Well, it's improving because it's going down below 4.28. We can, of course, also experiment with, for example, let's leave R equal 2, but let's multiply eta by 10. Okay, let's make eta equal to 0.001. Let's see what happens. Okay, the system diverges. So a step that is too large is dangerous because something like this might happen. You are trying to find the minimum of this. You start from here. You follow the gradient, so you move in this direction. But if you take too large a step, you actually end up on a larger place somewhere else, and so on. And since this is a polynomial problem, derivatives tend to be larger and larger as long as you go away from your minimum. So the system tends to diverge very fast. So let's keep it as before. Maybe I can double it to see what happens. Okay, with 0.2 it still works. Another thing we can do is, okay, here I left. So here I pre-computed the VI and the DJ biases. But actually, rather than pre-computing as row and column averages, we can also put them in the gradient descent calculation. So consider them variables that we need to determine in the gradient descent step. In this case, it means that I don't want to pre-compute them. So let's remove B and D from here. The only thing that I am going to compute now is the overall arithmetic mean mu, but not the vectors, the bias vectors. Instead, I will start here with let's see. Well, I should have written that. Okay, so now I initialize B and D with random values, and I also compute the gradient of the function with respect to B and D, which is, well, easier than the previous computations because, let's see, okay, actually, if I want to take the partial derivative of E with respect to Pi, well, it's simply the sum over J of 2 times the same thing as here, so 2 times S, times the derivative of Bi with respect to Bi inside here, which is minus 1. For the same reason, the derivative of E with respect to Dj is the sum over I of 2 times S times, again, minus 1. So we can compute these partial derivatives and add them to the equation. So, as I have done for matrices C and P, I can do the same for vectors B and D and define the two partial derivatives, dB and dd, by initializing them as 0. And here, okay, I'm just increasing the derivative of B with respect to user I, the derivative of the error with respect to the B and the bias of user I, by adding, okay, it was 2.0 times S times minus 1. So minus 2.0 times S. For the same reason, the same increase is added to the derivative with respect to dj. After computing those derivatives, of course, I apply them by subtracting eta times the derivative of the I, and equally for all items I do the same to the item bias Tj. And this should be it. Okay, so now I did not predetermine di and dj, but I leave the system to compute the best values for them. Let's see what happens. Okay, so as before, values are reducing. Let's see where they get. Okay, so now the reduction is more significant than before. We can hope that we can also go below 4. Well, at least if we continue with the simulation for more than 100 steps. Okay, what can we do about this? What can we do? How do we use the recommender system? Now, suppose that you are asked this. So, from the matrix A, for example, you can get to know what is the joke that was most appreciated by some user. The question now is, what other joke should I recommend to the same user to make him laugh as much as possible? And this system now can answer this kind of questions. In fact, for example, we can, well, let's just try to find what joke will be the most appreciated by any person. I mean, let's see what joke we should recommend to which person in order to have the highest appreciation possible. What can we do? After iterating and reducing the error, we can just let's see. Well, for example, we can compute the complete matrix of estimated joke appreciations. Let's call it A1. We want to build a complete matrix, so let's start from an empty list. I want to build it as a list of rows, of course. And now, for every user I, and for every item j, I want to compute the expected vote of user I for item j. So the vote A will be, well, we can take it from here. So estimated by mu plus bi plus dj plus the sum of the dot product of c and p. Let's build the matrix line by line. So A1I is the current the line being currently built. So here A1I receives A1. And after I compute the whole line, I add A1I to the matrix A1. Now the matrix A1 contains the whole expected appreciation of users to jobs. Next, of course, I want to remove all jokes that have already been rated by users. In fact, I don't want to recommend to a user a joke that he has already seen. So I can simply browse through the original matrix A and put some value here that encodes the user has already seen that joke. Let's see, it's minus 99. Now I am ready to find the maximum of the remaining votes. Let's say that I want to find the maximum for every user and for every item, maybe. So let's see, we want to maximize to find the maximum value for every row I. Let's call it max C, max customer, which is initially a list containing, let's see, suppose that it's going to contain the index of the maximum, so we can initialize it as 0. How many? Okay, as many users. The same for items, products. And now, for I in number of users, for j in number of items, I just of course, if a1 of I, let's call lowercase a1, small a1, the vote expected by user I to item j. So if a1 is better than the best rated joke by user I, we store it in max C. And we do the same for the items. This is max P. At the end of this loop, max C will contain the index of the best joke that should be recommended to the user, and max B contains the index of the joke that should be recommended to. No, the max P contains the user to which a joke should be recommended. So, for example, we can iterate on users in range n, and we can write I don't know, user is so recommend joke %d to user %d expected vote %f new line. And here we put the job number, so max C of I, the user number I, and the expected vote A1 of I, max C of I. Okay, let's also import sys. Now let's see what happens. Let's just do 10 steps, just to make things faster than. Okay. So here, okay, we have too many users actually, but we know what joke we should recommend to every user with the expected vote by that user. You can see that sometimes the expected vote is minus 99. This means, of course, that that user has already rated all votes. So his row only contains minus 99. In fact, you will remember that in the original file, there were some rows that started with 100, meaning that all jokes have been rated by that user. It seems that joke 88 is quite popular. Why is this? There might be two reasons. Either it is very popular, or the evolution of the system, I only made 10 steps, did not reduce enough the joke bias, the item bias, which was possibly set to a higher number by the random initial assignment. So probably the fact that joke 88 appears a lot is just an artifact. In many cases, the steepest descent algorithm also works. Let me copy these lines. Instead of assigning random numbers, let's start by assigning zeros to everything. Let's see if things do change. Well, actually, joke 88 looks very popular. So actually now I'm curious to see what joke 88 is. I should have somewhere the actual texts of the joke. Maybe I will put them in the on the course web page. Anyway, let's increase the number of steps now. Sorry, 100, and maybe we do 5. Steps here. Let's put some numbers, some formats here so that everything is in column. And here, rather than printing the error, let's format a line here, which is, for example, the step and the error with a few spaces and just a carriage return. Okay, probably forgot a parenthesis here. Okay, so let's see what happens after 100 steps of this. Okay, so this system can answer basically two questions. I have a customer. I want to recommend him an item. Which item should I recommend to have the best response from him? The second question is, I have an item that I absolutely want to sell. What customer should I recommend it to in order to maximize the probability of selling the item? And of course, another possible question is, okay, I have these users and these items. How do I maximize my revenue? So, what the item user do I pick in order to send a proposal, in order to maximize, of course, the appreciation of the item by the user. Okay, so joke 88 remains actually very popular. Okay, so I think that that it's more or less everything for today. Well, not for today, for this year. And so, as usual, I will take this code, I will comment it and put it on the website. The first written proof will be next Wednesday, maybe. I think June 6th. Let me check. Okay, Wednesday, the 6th of June. You have a pair of, you have two texts of the written proof of the last year to check on the website, plus some exercises. If you have anything to ask, of course, you can, well, if you come to my office, chances are that you won't find me, so write me an email. We can meet. Okay, I think that's all.